Okay, guys, welcome. Today we're going to talk about some certain special properties of logarithms. These properties are going to help us to be able to solve exponential and logarithmic equations in a future video. So let's go ahead and we'll get started. So just one sort of vocabulary thing to take care of is what we mean when we say the argument of a logarithm, right? Now, if you're looking at a logarithmic expression, you typically have something like log base a of x, right? Now, whatever that x is, whatever the thing is of the logarithm, that's what we call the argument. Right, so you can sort of think of it as the inside of a log, right? So that's an argument of a log. And of course, we know that the domain of a logarithm is all positive numbers. So we're always going to assume that the argument, regardless of if we have variables in there, we're going to assume that it's only satisfied for values that make the argument positive, right? So I'll typically refer to the argument of a log as the inside of a log, but if I say argument, that's what I mean as well. All right. Now, the first property that we're going to discuss when it comes to logarithms is the product rule. And that says that if you have a logarithm of a product, what you can do is you can separate those with addition, right? And sort of the reason why we're allowed to do that is that if you do the same, and of course this works for any base, if you do sort of something similar for exponents, if you multiply two exponents with the same base, what of course do you do with their exponents? You add them, right? So in sort of this convoluted way, you have multiplication leading to an addition of some kind, and that's sort of where this rule sort of stems from. Right, so as a couple of examples, if you have log base 3 of 6 times 7, you can say that that's log base 3 of 6 plus log base 3 of 7. You can separate them with addition, right? And of course, if you have more than two factors, you can of course extend this, right? So if you have log base a of x times y times z, you can just add those three things together, right? Now, I think it'll be easier to present a couple of these rules and then just go through a bunch of examples. So that's what we're going to do. Now, just like we have a product rule for logarithms, we have a quotient rule for logarithms. And that says that if we have the quotient inside of an argument of our logs, that means that we can separate them with subtraction, right? And again, sort of a similar thing comes up in exponentials. If you divide two numbers with the same base, you subtract their exponents. So sort of in some kind of way, we have division leading to subtraction. So it's sort of a similar analogy here. Okay, and one last example is that if we have the log of something to a power, we can bring that power out front, right? And of course, the corresponding exponential version of this is if you have something like ax to the n, what do you do with these exponents? You multiply. So sort of you have power becoming multiplication sort of in a similar way here, right? Now, one thing that's important to keep in mind is that if you have square roots, you can write them as powers, and those powers can then come out front. So that's one thing that we can keep in mind. Okay, now the reason why we have these couple rules here are so that we can expand and later condense logarithms. So when we expand logarithms, what we want to do is apply these properties until they're inside of logarithms don't have any products, powers, fractions, any non-prime numbers we would want to separate, and any roots we would want to get rid of as well, as they're just really a form of a power. All right. Now, one thing that you will notice is that if you have terms separated with addition or subtraction, you can't do anything else with that. Like for example, up here, you have this log base 8 of z plus 3. We can't do anything else with that, right? Because of this plus here. Now, in this case, we wouldn't be able to do anything anyway, but even if you had something like log base 8 of 2z plus, let's say, 5, right? Now, you might be tempted to take that 2 and separate that from that z, but since you have this plus here, that's preventing you from doing that, right? So if you have pluses and minuses separating terms, we have to be a little bit careful. Okay, but let's go through a couple of examples. So in this first one, of course, we see right away that we have division, so we can separate them by the quotient rule with subtraction. We could say this is log base 6 of 38 minus log base 6 of 71. Now, I believe that 71 is prime, so we're not going to be able to do anything with this one. So this one is done. Right? But 38, we can definitely break apart because we can say that 38 is 2 times 19. So we could say this is log base 6 of 2 plus log base 6 of 19. And then, of course, minus log base 6 of 71. So then that's our final answer. Right? There's no more products, there's no more powers, there's no more fractions. All three of these numbers on the argument of our log are prime, and there's no roots. So we're fully expanded. Okay, let's look at another one. So in part B, we see right away that we have multiplication. So we could say this is log base 7 of 15 plus log base 7 of 136. Now, of course, 15 we can think of as 3 times 5. So we can think of this expression as log base 7 of 3 plus log base 7 of 5. All right, so now the second one will be a little bit more difficult because I don't know, I can't see anything right away to definitely break it out to, with the exception of 2. Because it is even, so I guess we could do 2, and let's see, so 2 times 70 would give me 140, so I guess 2 times 68 would give me a 136. Right, so then it looks like we could separate that into a log base 7 of 2 plus a log base 7 of 68. But of course, 68 we could break into, I guess, a 2 and a 34. So we could break this into log base 7 of 2 plus log base 7 of 34. And I think we could do it one more time. I think we could say this is 2 times 17. So we could say that this last one is log base 2 of 2, sorry, log base 7 of 2 plus log base 7 of 17. So it looks like if we collect all of our like terms, get log base 7 of 3 plus log base 7 of 5, and then we have 1, 2, 3 log base 7s of 2, and then it looks like we get at the end, we'll finally get a log base 7 of 17. Okay, so there's our final answer there. Okay, so moving right along in part C. So first thing we notice is the 1/6 power. So let's bring that out front. We have log base 9 of 24. Now, of course, 24 we could break into 6 times 4. So this is a 1/6 parenthesis now, because a 1/6 is times both of these things. Log base 9, sorry, of 6 plus log base 9 of 4. And of course, each of these can be broken up. This is 1/6 log base 9 of 3 plus log base 9 of 2. And then this one will also be log base 9 of 2 plus log base 9 of 2. And then we get 1/6 times log base 3. Sorry, keep saying that. Log base 9 of 3. And then we have 3 log base 9s of 2. So then there's our fully expanded form for this one. Okay, now these, of course, are, well, they can get sort of out of control because you could be taking prime factorizations of numbers and essentially, you know, really boiling a number down. Like, for example, that 24 basically became 4 different factors that we had to consider. Now, something that's more realistic is something like this one. You now have variables involved. Now, of course, the first thing that we see here is you do see the power here, but it's not applied to the 5. So the first thing that jumps out is this multiplication. So that's what we're going to handle first. So this is log base 3 of 5 plus log base 3 of x plus 1 to the 4th. So now the 5 we can't do anything with. 5 is prime, but in this one we can bring the 4 down by the power rule. So we have 4 log base 3 of x plus 1. So it looks like our final answer is log base 3 of 5 plus 4 log base 3 of x plus 1. Okay. Now part B, you may see the fraction right away, but since the 5 is being applied to the whole fraction, we're going to worry about that first. So this actually is going to become a 5 log base 8 of 9 minus c over 2. All right, so now we can deal with the fraction. We have a 5, and then, of course, parentheses, very important here, log base 8 of the top, which is 9 minus c, minus log base 8 of 2. All right, now we can do one more thing, but it's a little bit subtle here. This log base 8 of 2, we can do something with, because if we were to do this off to the side, log base 8 of 2 is equal to x. Well, this is 8 to the x is equal to 2. So if we write this both sides with the power of 2, we get 2 to the 3x is equal to 2. And since this is 1, we get 3x is equal to 1. So x is 1/3. So we can actually plug in a 1/3 in for this part here. So finally, we get 5 log base 8 of 9 minus c minus 1/3. All right, so that will be the fully expanded version of this one. So anytime you can sort of easily do that simplification there, that's usually generally something that we would want to do here. And I probably, right, you could do something similar for this one here, all right, but I missed that one. And I think that might be the only one that I missed, right? Yeah, that would be the only other one that would work out easily, but that's something that you can always go back and verify. Okay, now we'll do one more expanding, and then we'll take a look at condensing. Now here, again, you see a fraction, you see a power, and you see multiplication. Now, since the fraction is sort of the outermost function here, right, the exponent is only being applied to the 2 terms on the top, and the multiplication only applies to the 2 terms inside those parentheses or those brackets. So the first thing we want to do is the multiplication or the division. So we have log base 7 of the top, so x times x minus 8 squared, minus log base 7 of the bottom, so 6. Now on this part here, we can bring the 2 out. Log base 7, x times x minus 8, minus log base 7 of 6. And now, of course, if I use my parentheses carefully here, we can say this is 2 log base 7 of x plus, so it's going to be a multiplication, log base 7 of x minus 8, close my parentheses, and then minus log base 7 of 6. And that's the best we can do there. All right. So that's sort of what we mean by expanding these different logarithms. Now, more importantly, and luckily it's a little bit easier, we're really more concerned with how to go the other direction. We're really more concerned with how do we take a bunch of logarithms and condense them into one single logarithm. So going the opposite direction that we've just spent the past few minutes doing. So generally this is a little bit easier because there's more of a sort of set thing that you can follow. And of course, you know you're done when you have a single log remaining. That's the whole goal of this. So condensing logarithms, the goal is to combine into one single logarithm. Right? So in general, you're going to apply the power rule first. So any numbers that are in front of a logarithm will now become the power of the argument of that logarithm. Now, any logarithm that's positive, you're going to find all those, you're going to multiply them together in the top of a fraction. And any negative log terms, you would take their arguments and multiply them together in the denominator. All right. So here's what I mean by that. So in part A, again, first thing that we generally want to do is apply the power rule. So this 4 is going to come up top. And we have log base 5 of m plus 3. And this is now going to be to the 4th power. All right. Now the 2 on this term will become this power. Now, since both of these are positive, we're going to multiply them together. Or I should say multiply their arguments together. And now write this as a single log. It's going to be log base 5 of m plus 3 to the 4th times n squared, right? Both of these terms are positive, so we're going to multiply their arguments in a numerator. And if there's no denominator, it's just going to be multiplying them together. All right, now in part B, same idea. The first one doesn't have a power. So this was second here. All right, so the first step, this one doesn't have a power, but of course this one does. So we can take the 3 and make it the exponent of this argument. And now since the top term, or sorry, the left term is positive, that is going to go in the top of the fraction, and then the x minus 1 to the 3rd will be in the bottom. And then that's our solution there. All right. I think this is the last example, right? Well, one more example, and then we'll talk about one last property, and then we will wrap this video up. So in this one, again, we'll apply the power rule first. We have log base 7. This one doesn't have a number out front, so that's just going to stay. This 2 in front of this logarithm will become this exponent, and the 3 in front of this logarithm will become this exponent. All right, so now these first 2 terms are positive, so they will go in the numerator. So I have log base 7. Now on the top, we are going to multiply x plus 1 times x plus 4 squared. And since this is negative, this will go in the bottom. So we'll have an x minus 5 to the 3rd in the bottom. All right, so there's our final answer there. Okay, one last quick property that's not too difficult, and this will be an important property when we look at equations involving exponentials and logarithms, because this is going to allow us to essentially cancel out exponentials and logarithms, right? And these are really sort of like the inverse properties. Right, and this says that if you have log base a of a to the x, that's just going to give you x, right? And of course, this just comes from converting to exponential form, if you convert this, you get a to the x equals a to the x. All right, so that's easy to see. And this one, you have a to the log base a of x is equal to x. And if you convert this, this says that again, log base a of x is equal to log base a of x, right? So what does this mean really? Well, if we see it sort of in slow motion, you can see that the answer is going to be 2 by these properties. But if you don't believe that, just convert it to exponential form. And you would say, well, 7 to the x is 7 squared. And if 7 to the something is equal to 7 to the something, then those two somethings better be equal. So then we get x is equal to 2 here. Right, and last but not least, this is just the other property. If we say that this is equal to x, and we convert this to logarithmic form, this tells us that log base 3 of x is equal to log base 3 of 12. And if log of something is equal to log of something, then those two somethings better be equal. Right, so that's sort of the long way of seeing that if you have a log of a certain base and an exponent of a certain base, they're going to essentially undo each other. Right, so that's what these properties are showing here. All right, so that wraps this video up on properties of logarithms. I hope you enjoyed, and I will see you next time.